So the conventional assumptions, as we have seen over and over, are that capital and labor are gross complements in both like the production sector and the tech sector. Meaning, sure, in some simple models, the elasticity of substitution might be constant, but even if you have a richer model in which it varies, it's bounded below zero. You can't send output to infinity just by piling up either of the factors in isolation, in particular capital. Oh, sorry, yeah, this was introduced, I think on Monday. That's a row, so that's a substitution parameter, and the subscript is just denoting which sector we're talking about. So like the production part of the economy and the R&D part. Oh, you're asking, yeah, the B. Yeah, sorry, I heard P, sorry. The, yeah, so bounded below zero means there's something negative that it stays below. So it's not just always negative, but it doesn't approach zero, right? Because you could have like you could have a sequence of local substitution parameters that approaches zero, and then kind of in some asymptotic sense, you're basically Cobb-Douglas. So today, we'll be assuming that labor remains necessary for R&D, but considering scenarios in which capital and labor become gross complements, either just because of an exogenous development of sufficiently labor substitutable capital, so like AI systems and robots and so on, or because maybe the elasticity of substitution as a function of our factor and technology terms all along has allowed for gross substitution if you had a high enough capital to labor ratio, say. And so locally, looking at the economy now, it looks like they're strongly complementary, but as we get richer, we'll just sort of naturally, endogenously transition to a world of gross substitution. So we'll consider that as well. And then finally, we'll consider what happens when there's a natural resource bottleneck. There's like a kind of capital that you can't accumulate, but is only in fixed supply, say. We'll see what changes from the above. And we'll mainly be considering impacts on these three big macro variables: overall output, the fraction that gets paid in exchange for labor, and the product of the two, which is the aggregate wage bill. Right? So historically, of course, B has been constant. So A and A times B have grown at the same rate, more or less, as output been growing at 2% a year, so have aggregate wages. But if the labor share changes, then that won't necessarily hold. Well, the wage bill could even fall if the labor share falls more quickly than output is growing. For the most part, because we're not really dealing with R&D here, this substitution parameter without a subscript will typically denote the substitution parameter in production. Okay. So just first, briefly, why are we jumping all the way from the world of incremental task by task, job by job, age by age automation we've been focusing on for the last few days, all the way to a world in which we've got kind of gross substitution down the line in production? Well, first, because as you probably heard, some people think that we might be making that leap before too long. Lots of prediction market evidence and survey evidence from different sources just testifying to the fact that people believe this, not making a case for it. We'll do a little bit of that next week. Yeah, just briefly, so some people at AI Impacts, Katja Grace et al., have a few times now done a survey of top AI researchers. The most recent one was in 2023, or at least the most recent published one. And they seem to think that there's a 10% chance that all tasks a person could do would be automatable by 2027. So we're already halfway to 2027 from when they were surveyed. I don't know how they'd update, but so they thought there was a whole 10% chance and a 50% chance that it would happen, within our lifetimes, hopefully. And a 10% chance that all work would be automated, by 2037, median 2116. Incidentally, the fact that the answers are so different, especially for the median, really illustrates the limitations of a task-based model, right? Like, at least these AI researchers think it could totally be the case that we have systems separately that could do, every, I don't know if they think about ONET task, but like every kind of intuitive task that a person could do, but you'd still want a person for occupations for a while past that, presumably because it's just more efficient to have like the same system doing lots of tasks at once. Yeah.
So
okay.
Works created some tasks, right?
Well, they are in a kind of simple task-based model like we've been looking at, but I don't know if you remember, I mentioned that there were some limitations of the task-based model. Remember my Pamela Mishkin example? So maybe there's a difference between a job and just the set of tasks that go into the job, and maybe what that difference is that you can learn how to do some of the tasks better because of the context that you get from having done the other tasks. And so even if you have tools that can individually do all the tasks in isolation, you'll still need a conductor for the orchestra. Okay. Note that this is a forecast of when like all work will be automatable, which is a weaker condition from how much automation you need to deliver some of these really transformative effects, in which growth starts to skyrocket, as we'll see, but as you can probably intuit, where once you relieve all the bottlenecks, growth starts to skyrocket, the labor share falls, and so on. This is because you can imagine some jobs which at least it's logically possible that there would be some jobs that only a person could do, and so we wouldn't be satisfying the all work automatable threshold, but which are not so necessary, right? So growth is not bottlenecked, right? So just like as a silly example, if for some reason only humans could make spinach and mushroom pizza, then like not all work, but like machines could do everything else, and not all work would be automatable, but I doubt we would. That would bottleneck growth. Like we'd all pour all of our GDP into spinach and mushroom pizza because the other stuff is so substitutable. We would, we would just consume more of the stuff that's easy to produce now that machines can make it. Okay. All right. So, but then on the other hand, you might not get the explosive growth even after all work is automatable technologically because of, licensing rules or something. So technically the survey is about something a little different than what you might care about economically. But all right, just to dig into that a little bit more, these are the sort of confidence intervals you get by aggregating the forecasts. I won't get into how they do the aggregation. But one interesting thing is that when you ask about these different milestones, their median and their whole range of guesses for when AI research will be automated is kind of basically it's like the last profession, right? Truck driver is like one of the near-term ones. And equations governing virtual worlds, I think that's basically what we're doing here, is at the very bottom. I think they might be kind of right, but also I think maybe the complexities of your own work are better understood. And when you see, some, morons down the hall governing virtual worlds with their equations, you think, okay, that can't be too hard. Here's a kind of graph showing what the timelines look like for the tasks. So you can see the 2023 survey has for instance whatever, like a 20% chance of all the tasks by 2050 and so on. And you can see that the timelines were much shorter in 2023 than in 2022. I think even the AI researchers were kind of surprised by ChatGPT. Likewise, Oh, no, wait. Sorry, these graphs are flipped. HLMI is what is meant by all tasks, and full automation of labor is what's meant by all work. So yeah, sorry, get that? So sooner timelines for all tasks, later for all work. Okay, yeah. Can you mark that down? I've got to flip that. Thanks.
One of the tasks is orchestration. Should be, because CEOs also have some tasks.
Yeah.
Shouldn't, once we have, like, I get that the one of them first order stochastically dominates, but it should reach the singularity at the same point.
Yeah, it's a good point. I think they must implicitly be thinking of some different limitation of a task-based model than the one that Pamela was getting at. Because in the Pamela example, once you have machines that can do the Zoom call and the email, then they're going to then you got to automate both. And yeah, like I was saying, the prediction is that you would get maybe full automation around the same time, but it would happen more suddenly. Yeah, it's a good point. So maybe they're just not really thinking about all the tasks that go into orchestration. Or I don't know how they're interpreting the words of the questions. Thanks. Okay, so let's say we move to a world of gross substitution, right? Now, yeah, and labor, the population could be growing or not, and labor augmenting technology could be growing or not. The first kind of choice point to recognize is whether you think the level of capital augmenting technology will stay fixed or whether it will start growing. So we know from Mazlish's theorem, historically, it has not been growing. And you might think that even after full automation, it will stay fixed as well. First, you might think that because if you remember the automation model, right, the task-based automation model from Monday morning, the whole reason why we've been getting this labor augmenting technology within the story of that model is because we've been incrementally automating tasks, right? It's not that we've been like coming up with stimulants that get people buzzing around the factory twice as fast, even though it might kind of look like that in closed form. What's been happening is that we've been crowding people into an ever narrower range of tasks, and so each drop of water has had to sort of be spread over a shorter range, and that's been, amounting to labor augmenting technology. And if that's sort of what's been going on, if that's all that we can do, then once you get to full automation, you have y equaling AK plus BL, but there's no more tech growth, right? Capital just accumulates exponentially. You get exponential growth, it'll be faster, right? Given the sufficient saving condition. The bottleneck before full automation was a lack of automation, lack of labor augmenting technology. So you'll have robots building robots, and you'll have some exponential growth rate that's faster than the old growth rate. But A itself will not be growing. You might also think, okay, well, Mazlish's theorem just tells us that the degree of kind of aggregate capital augmenting technology has been constant for a long time. And even if we don't understand exactly why, it just suggests that there's some hard, even if non-obvious constraint on what you might call the reproductive rate of capital. On the other hand, think about what high A means within a model like this. It means sort of quickly self-replicating robots. And they don't actually have to be self-replicating individually. It's not like one robot needs to like build its own robot babies. The whole economy, the whole like network of supply chains just has to be such that it reproduces itself quickly. But even if we restrict ourselves to the thought experiment of machines building more machines like themselves using the resources they have to go and mine and build little factories to implement a plan or whatever, we know there's not like some really hard limit keeping A down at the low rate that it's been at for a long time, from the fact that there are some pretty intelligent animals like octopuses that can reproduce immensely quickly. So in the case of octopuses, it turns out that the female ones have about 250,000 eggs. They mate, they fertilize the eggs, they spew them out, and then they die. And so there's no parenting that goes into raising the octopuses. They're just like seeds that are scattered to the wind and planted. And most of them get eaten, but or just die young. But if you imagined, a kind of octopus, in a resource-rich world that didn't have any predators or anything, then it would be growing at like 250,000. Oh no, wait, I think it's that they have 500,000 eggs, and they live for 2 years. So, yeah, so the growth rate would be 250,000 eggs per year. Anyway, yeah.
I feel like I missed something about A. Like I'm thinking in the last century, didn't we improve material science? Shouldn't it at least increase A with the constancy of A?
Yeah. No, that's a great question.
I feel like they're missing something by coursing all the TFB into B. And
yeah, so I'll get to that on the bullet right below this, but I'm just sort of like noting a thought you might have, which is like, okay, well, it sounds weird, but apparently in aggregate A has been constant. But I'll get to your thought at the bottom.
One thing I was just talking about earlier in the review session of the Jones-Cincinnati model is you can think about there being capital task quality improvements, which are increasing A, but at the same time, the fact that we are having automation is capital depleting, and maybe those two things offset so that aggregate growth in A is roughly zero.
Yeah, that's an example of what I'll say a few words about in a moment. Yeah, a next sort of reason to think that like we would shift over to increasing this sort of reproductive rate of capital in the event of gross substitution is that the reason why maybe we've been focusing on sort of changing our production processes in a more labor-saving way rather than a capital-saving way is because you need both things, effective capital and effective labor, in the gross complements world. And we can pile up the capital pretty quickly, and the effective labor is, with the fixed population, it's not going to grow unless we put the work in to develop technology that's labor saving. And yeah, population is growing a little bit, but not as fast. So yeah, see that? So the primary incentive in that world is going to be to develop labor augmenting technology. Whereas when you switch to the gross substitutes world, when y equals AK plus BL, then at least sort of if K and L start out equal, then there's, the profit, your profits go up just as much if you increase A a bit as if you increase B a bit. And in fact, in the long run, when capital is much more plentiful than labor, basically all your inventive effort will go into like trying to augment the plentiful factor rather than the scarce factor. So Acemoglu in 2003 has this like seminal paper on making this point about how we will tend to shift our technical change in the direction that relieves the bottleneck that's, sort of makes effectively more plentiful the scarce factor. And I think it's probably worth going through. We're not going to go through it because the particular assumptions he makes that sort of ensure that Uzawa's theorem will hold precisely are a little bit ad hoc maybe, and I feel a little bit knife edge, and I think it's still a little bit of a mystery. My understanding is we still don't have a great sense of why exactly historically directed technical change would have resulted in such an exact maintenance of this constant A. But qualitatively, at least, I think the point's pretty robust, right? Like you're going to expect a shift from B to A as we moved from gross complementarity to gross substitution. Yeah. Oh, it's just coming from the fact that if like, let's imagine perfect substitution rather than just gross substitution. The logic's going to basically be the same. So you've got y equals AK plus BL. So what's dy dA? That is, how much extra output do you get to make with your factory if you come up with a way to make your capital more productive? Well, that's K, and dy dB is L. And you've got a more or less constant set of humans, but you've got an ever-growing number of robots. So if you can come up with a way to make each robot more productive, that's going to pay off better than coming up with a way to make each human more productive. Yeah.
So my understanding is that pre-AI revolution, we feel like we're in the complement space, those complement space.
Yeah.
And I thought not the scientific work, but the extra academic work Gemolo has done is more like, all the technology is capital intensive,
yeah.
capital augmenting. Is it the monopolistic incentives that is driving it for a few firms, rather than the broad production function issue, or is it a positive general?
No, well, I mean, again, I think why things have aggregated as sort of exactly as they have is a bit of a puzzle. But okay, I guess I kept promising something important at the end of this slide, and it's not going to be as, it's a little bit terse. But anyway, what I was going to say is, yeah, another reason to think we're going to get more efficient capital is that we clearly do get more efficient capital for particular kinds of capital already, right? So like famously with Moore's law, like we're able to have each unit of silicon crank out way more computations every year. And like, yeah, Huang's law or whatever you call it, it's even faster maybe with GPUs. So what's going on with the fact that when you look at like producing, like getting particular services out of particular lumps of capital, we're increasing our productivity, and yet in some aggregate sense, it hasn't been rising. It's presumably some combination of the fact that we are developing, like, yeah, fixing the like narrow service that the capital is providing, it's getting more productive. But as time goes on, we develop production processes which are labor saving, but which are way more capital intensive. So you need way more like kinds of machines and things than you needed before. And so the amount of capital you need per unit of output is staying the same. But it would have been falling, the amount of capital you needed for a unit of output, if we just restricted ourselves to like whatever, making computations or something.
Would it be rho IT is positive while rho services is negative?
Well, I don't think that's right. I mean, when you say rho IT, you mean like in the...
Have a nest of certain sectors as a final good, but then each nest use capital and labor, each capital and labor nest has its own...
Yeah, I see what you're saying. Okay. So you're saying like in the production of compute, you're thinking maybe capital and labor are gross substitutes? Yeah, I think that's probably not true. Like, yeah, it seems like work is necessary to build fabs and then to work the fabs to build chips and so on. It's not like we've gotten to full automation. In fact, this afternoon I'll show that we have not gotten to full automation or anything close to full automation in the production of IT capital. Oh.
So bear with me because I'm like so confused that I don't know how to test.
Oh no.
And it's very basic. Isn't it the case that like if the production function was called Douglas, then it kind of like doesn't matter.
Yep.
Right? It's
Yep.
just like the same thing.
Yep.
And to even like talk about the stuff where like assuming it's not called Douglas.
That's right.
Okay.
That would be Asimovoglu's. Well, okay. Yes, is the short answer.
Okay.
Yeah. But I mean, I do think that's probably right. Okay, so we'll be thinking about a shift to full automation or to gross substitution at least, and mainly be thinking about the case where, for whatever reason, now A is growing exponentially. but we won't be thinking about the production function for A. We'll say, you know, with a world of full automation in production, and then just in the background, you've got A growing exponentially. But I'll leave open the possibility that A is fixed after all. Because I don't know, it might be fixed for a while, or you might believe these arguments. So that's what we'll do. So as I said, there'll be three variables that we look at mainly: growth, labor share, and the product of the two, wages, the wage bill. As for growth, recall that as long as we've got our sufficient saving condition, the growth rate, you know, you basically, we move, once we switch from gross complementarity to substitution, the growth rate moves from the minimum of those two to the maximum. So given that the minimum is currently growth in effective labor, you know, as long as we're not kind of right at that knife edge condition, like the first off effect will just be, we'll have an increase to the growth rate, fixing A, even fixing A. Make sense? The capital's been kind of outpacing the effective labor. I mean, it's not really been outpacing it persistently because you need to, you know, replenish the capital as it depreciates with past output. But the capital's been not the bottleneck. And then once you relieve the labor bottleneck, the capital will grow at some higher exponential rate. So yeah, output per person will also grow at a faster rate. Now, fixing the savings rate, if you forget everything else, I would just remember this. Output in a gross substitution world is basically AK. Okay, like, yeah, there's a little bit of complementarity. It's not completely constant returns to scale. Output's not completely constant returns to scale in capital, but it's basically constant returns to scale. Because remember, fixing labor, the gross complements world has output growing like, you know, output growing in capital as you pile up the capital only to a ceiling. The Cobb-Douglas world is where it grows without bound, but at a rate that like falls to zero. And so depreciation eventually, you know, slows you down, like it's like square root or something. But the gross substitutes world, there's like the extent to which output is not just linear in capital, that deviation induced by the fact that you're not doubling the labor alongside the capital, that deviation itself just shrinks as you pile up the capital. So its output looks kind of like this in capital. So once you've got a lot of capital, basically y equals AK. And yeah, so what that means is, as we just said, fixing A, the growth rate rises, but that's just a one-off rise. But with exponential technology growth, the growth rate itself rises exponentially. So you have double exponential growth. See that? You start out with one robot, no tech would be 1, 2, 4, 8, 16. But with each robot getting more productive every year, the exponential growth rate itself will rise without bound. And it'll, you know, it'll rise exponentially if GA is some constant that's positive. Incidentally, this means that like you don't need to worry about that sufficient saving condition. As long as the savings, well, you have to worry much less about it, because for any stream of savings rates that's bounded above zero, eventually, in fact, that pile of effective capital will be growing faster than the effective labor, right? Because S can be really small, but A is growing. So yeah, as long as A grows without bound, eventually AK will be growing faster than B. You don't need A to be growing exponentially for that. And then also, we don't really need to think much about depreciation. And the kind of simple intuition there is that as long as the rate of depreciation is not going to infinity, so you know, you're getting like 100% depreciation every second or whatever, you don't need to worry about it, because basically with super exponential growth, the capital stock eventually consists almost entirely of capital just produced recently. Does that make sense? With exponential growth, the like average age of a bit of capital you have is just going to be constant. over time. See that? You've got a pile of capital, you produce 10% more this year and you add it to the pile. So 10% of the new pile is a year old. And then the next year you increase the pile by another 10% and you add it, and then, 10% is a year old again. And, 1 minus 0.9 times 0.9 is 2 years old. And so, yeah. So, depreciation might matter in the exponential growth case. But with output growing super exponentially, in this case double exponentially, then, eventually the ratio of how much you're producing now to how much you've accumulated over the past is growing without bound. And so a larger and larger fraction of the capital stock is recent. Any questions on that? That's fixing the savings rate. Now, kind of as an aside, but I think it is good to know about and think through carefully. You might wonder if the savings rate could fall quickly enough to diffuse the double exponential growth made possible by exponential growth in A in a growth substitutes world. Now, it turns out this isn't possible with isoelastic utility. To see this, recall from that Sunday morning lecture that an increase in the kind of cumulative interest rate that you get by big R, remember, is like how many dollars you get at time t if you put aside $1 now, or like a real dollar in some sense. An increase to how much you can buy in the future with a unit put aside today is like a decrease to the price of future consumption. And yeah, this is going to be your Euler equation. If if an investor is indifferent in consuming a little more now and putting a little more aside till time t, it's got to be that the number of utils they get now from consuming more, which will be this, given isoelastic utility, equals the discounted number of utils they get per dollar times the number of dollars they get from putting aside $1. And you can raise both sides to the -1 over eta, and then divide by CT, and then flip. Wait, multiply it by -1 over eta. Yeah, and then flip. Good. Yeah. Okay. So the ratio of consumption at some future time to consumption today is going to really depend on what that interest rate is. And observe that the number of dollars you get at time t for $1 put aside today is going, because we're basically in an AK world, maybe this should have been an approximate rather than an equals. But because we're basically in an AK world, you integrate. In general, this is a good thing to know if you're not familiar with it. If you know what the growth rate of some variable is, point by point in time, then how much you grow from now to any given future time is e to the integral of that growth rate at each point in time. So you can take logs and think about the logic of that if you want. But given that, you see what we're doing here? We're integrating kind of the interest you get from each dollar you've put aside at each time tau. And it's a pretty simple integral. You're integrating something exponential from 0 to t, and that's what it ends up equaling. So the interest rate is itself double exponential, which makes sense. I mean, it's sort of, because obviously the instantaneous interest rate's going to be growing exponentially. Since R is growing double exponentially, so how many dollars you get at some future time is a double exponential function of how long you wait. We see from that formula there that the ratio of future to present consumption is also going to have to grow exponentially for you to be on your Euler equation. Okay? So we'll be in a world where, what people consume is growing double exponentially. At any point in time, if you like pause the movie and say how much are they consuming now, and then ask how much will they be consuming at some future time, the ratio is going to grow the ratio is going to grow double exponentially in how further ahead you're thinking for any initial frame, for any initial time zero. That make sense? Okay. Yeah.
Still 100% clear. What exactly does double exponentially mean?
Oh, it means that you have an exponential rate, which is itself growing exponentially. So let's say the growth rate starts out 2% a year, like something like what it is now when we first introduce the robots. The growth rate will rise, okay, given growth in A. Now, how fast will it rise? Well, if it just rose linearly, that would not be double exponential. That would be linear exponential, because you'd have like 2% growth this year, 3% growth next year, 4% growth the year after that, and so on. Double exponential means the growth rate is 2%, and then say 4%, and then 8%, and then 16%. Great. So just plot time on the horizontal and the exponential growth rate on the vertical, and that is exponential, whereas currently it's just flat. Yeah, thanks for asking that. Now, this can be diffused, right? But only if the inverse elasticity of intertemporal substitution is itself rising sufficiently quickly. Okay? So only if we're kind of, in some sense, satiating quickly enough. And again, you can kind of see that because, R is getting big, if eta gets big too really quickly, then you're raising R to an ever smaller power, and that CT over C0 ratio might not actually grow that fast. People want to save less and less as they get richer. That might be kind of an extreme assumption, but there's another kind of qualitative point that could also be relevant, at least for a while, which is that the effect that we want to consume more now instead of saving when the interest rate goes up, that's not going to diffuse double exponential growth for any isoelastic utility function, but it could slow it down a bit. Like what the double exponential is could be pretty slow. If we start out at 2% growth, and then it's 4% after 100 years and 8% after another 100 years, that's double exponential, but it's really slow. So if like eta is really high, then you get that really slow double exponential. And this could especially be an issue if automation redistributes from high savers to low savers, okay? So Sachs and Kotlikoff have this working paper from 2012, which makes the point that maybe what'll happen with automation is that the working young, their incomes go down because their wages fall. We haven't talked about wages yet, but it could happen that wages fall. GDP goes up, but it's all in the hands of these retired old people owning the capital, and they're not saving very much. Maybe in this case, it's not because they have an especially high eta, but because they have an especially high delta. They're discounting the future really quickly because, well, if we get immortality, this could also flip. But anyway, so, or just, radical life extension or something. Yeah, so, the saving thing could be important over like a sort of medium horizon, even if you think that this is too extreme to like diffuse double exponential growth in the very long run. And then like, yeah, these two people and some co-authors have more recent work with much more complex models in which this sort of change in the savings rate as a result of the redistribution that comes along with automation plays a really central role. But I don't know. I feel like I don't get that much out of the more complex models. And their earlier working paper, I think, makes the core point very simply. Okay, so that's just kind of an aside about saving. A little bit more about it, though. So as you'll all remember vividly from the exercise that you all did, there's really not that strong of a basis for assuming isoelastic utility in the first place, or constant relative risk aversion utility in the first place. So what you were asked to work out was what utility function you would think people had if you observed linear consumption growth in a world with like constant long-run savings rate. It turns out the answer is constant absolute risk aversion utility that looks kind of like this, with some extra constants you can stick in if you want. And if our utility functions look like this, they're still going to be increasing and strictly concave and all that. They're going to rise toward an upper bound, like in the case of isoelastic utility with eta greater than 1. But they look like, it looks like this, right? So this is u of c and equals 1 minus e to the negative c. This is c, right? So when c is 0, 1 minus 1. When c is infinity, 1 minus 0. So yeah, this is going to be a 1. And as you can kind of see just by looking at the graph, up here it's concave. But around here, it looks pretty linear. Like the coefficient of relative risk aversion is going to be basically 0 down here. And it turns out, in fact, it goes from 0 to infinity. So in a sort of sense relevant to governing how people want to save, as they get richer, they want to save less in this case. And how much less? Well, so much less that if you write down the Euler equation again, now this is the marginal utility of consumption at time 0, right? So just differentiate that utility function. Pull down the negative on the c, you get e to the negative c. The 1 is a constant, it goes away. So e to the negative c0, that's your marginal utility at time 0. Likewise, marginal utility at time t. This is the interest, that's the discount. Take the log, and then add ct, and you get that. See that? So now we're looking at the gap between consumption now and consumption in the future. But anyway, that gap in the long run is growing exponentially. And so what that means is that consumption itself in the future is going to be growing exponentially, right? So yeah, non-completely crazy utility functions, I think, could motivate saving that slows over time in a way that turns a double exponential potential growth rate into a exponential growth rate that gets realized. I mean, it only takes one weirdo saving, at a rate bounded above 0 to pull the aggregate growth rate up to the potential double exponential level. So I don't think this would diffuse double exponential growth forever, actually. And we'll just put this aside in general. But just keep it in mind, saving can be important. And it's all the more important in an AK world. Yeah.
Speculate about how AI might affect growth rates, but do we already have something?
Well, I mean, there's sort of ingredients to this that you can test. Like you can look at whether savings rates have tended to fall as people have gotten richer or something. That I think is not true. But there's like 100 other things changing in the world over time, and it's going to be whatever. I'm not enough of an empiricist to have a good answer to your question, but I would say rather than trying to like directly estimate whether like the first little glimmers of AI we have today are significantly speeding growth or affecting savings rates or whatever, you want to probably dig a little deeper and sort of say, okay, we're speculating about a world of like something close to full automation, and what do we know about how production works in general and about what utility functions people have in general? What do they imply for what would change if we just swapped out like the negative row for a positive row? But yeah, maybe Zach, you got a better answer. Yeah, we went over this a lot in the morning session associated with this exercise. Yeah, I mean, I think that's so right. So a piece of evidence pointing the other direction is that richer people have higher savings rates than poorer people. There, I think, I mean, first off, just mechanically, people who save more are going to be richer. eventually. So it could just be like a level effect sort of thing. But then also, I think once you get to the very wealthy, the issue is more just that we don't have ways to consume that quickly now. And whatever. I mean, I'll talk more about this later, but my kind of view of the world is that at any given time, fixing the range of products available, utility does taper off pretty quickly. And even a middle-class person is pretty near the utility ceiling. And if you don't feel that way yourself, just ask, again, what a chance of death would it be worth taking to get a blank check? And yeah, I think it's not that high. And so what that means is that if you've just got loads and loads of money, then you just kind of slam up to the ceiling. And what do you do with the rest of it? Well, you hold on to it either for status reasons or in the hope that one day people will invent some way to, again, just like, yeah, crank your gullet open big enough to like, hose down consumption at a faster rate. By like, I don't know, inventing some expensive thing like a rocket ship to Mars or whatever. So the ceiling rises over time, but at any given point in time, it's really concave. But anyway, that's just something I believe. But yeah, thanks for raising that. Rich people have higher savings rates. Okay, so putting that aside, going back to the next big variable, wages. So, and then labor share will be last. So we talked about growth. What happens to wages? Well, you just differentiate output with respect to labor. And you get the 1 over rho that gets pulled down, but that cancels with the rho on labor on the inside. That whole big expression to the 1 over rho minus 1 is the same as y to the 1 minus rho, because y to the 1 minus rho is the thing in the parentheses to the 1 minus rho over rho, which is the same as 1 over rho minus 1. So line 1 is the wage. And it grows with output, at least unless rho is 1. If rho is 1, y equals AK plus BL, and a huge surge in output driven by effective capital is not going to raise the wage. But as long as rho is even a little bit less than 1, as long as capital and labor remain complements, not gross complements, but just complements a little bit, the fact that we've got ever more effective capital raises the marginal product of labor. And it raises it enough that the wage is always growing at a slower rate than output, okay? So the fraction of output paid as wages is shrinking to 0 exponentially. But output's growing double exponentially, so the wage is going to be growing double exponentially. Even fixing, even without any labor augmenting technology. Just imagine a fixed population for simplicity. Yeah.
I couldn't follow. Rho less than 0 is the gross complement.
No. So I'm saying, yeah. So I'm saying, so you've got different values rho could be. Rho can be, it can be like negative infinity in the Leontief case, the perfect complements case. But then this is the Cobb-Douglas case, and this is the perfect substitution case in which like y equals AK plus BL. Okay, and I'm saying if you move from where we are now to a case where rho is greater than 0, so you're in the gross substitutes world rather than the gross complements world, but you haven't gone all the way to the perfect substitutes world, then even though capital and labor are gross substitutes, they are still complements. So having more of one still increases the marginal product of the other a little bit. and you're having more of the one really fast. It's not labor depleting at all.
Capital augmenting, but wage decreasing case. That's what I was asking.
The wage is growing. Here, there's no depletion. I'm allowing, or I mean, you could imagine GB being negative, but I haven't been proposing that. I'm just saying, just forget about B. Let's say labor augmenting technology stays the same, and we shift over to increasing our level of capital augmenting technology. Okay, so Y is going to be growing double exponentially. And so the wage is also going to be growing double exponentially. But it's funny, we go from double exponential growth throughout this whole region in wages to no growth at all in wages, fixing, labor augmenting technology in the perfect substitutes case. So a little bit of complementarity really, really helps wages. I don't know where the time's gone. It's already 11:50. It's awful. Oh my God. Okay. Well, anyway. Okay, so anyway, so that's what I was saying. More capital, higher wages, except in the perfect substitutes case. What happens to the labor share? That's going to fall to 0. You can see that from the formula, but it's also really intuitive. You can see that in different ways, but the intuition just follows from the AK plus BL case. The two things are basically substitutes, and you have way more of the one than the other. So the fraction, like if these things are kind of serving the same role, the capital and the labor, and you just have way more of the effective capital, there's no way for the labor to maintain a large fraction of the payments, right? Because the robot's just as good as you and there's more of them. So okay, in summary, growth rises at least sort of as a one-off, but then it keeps on rising if we develop capital augmenting technology. Wages will grow double exponentially if you have even a little bit of complementarity, like bounded, maybe I should have put a little b there, but bounded below 1. But then in the perfect AK plus BL case, the wage just grows at rate GB as before, which means that it stagnates if we just leave B where it was and we shift over to making our robots rather than our people more productive. And the labor share is going to fall to 0, and it'll fall all the faster the more quickly we're growing the stock of effective capital. Just for a graph of what this might look like, Nordhaus has a 2021 paper we'll talk more about later, in which he considers the case of kind of just barely crossing a line in a way. So shifting to a world in which the substitution parameter is 0.2, we shift to growing our capital augmenting technology. It grows really fast, at least by historical standards, at a rate of 10% a year. Now that's much slower than the rate at which some kinds of capital have been getting augmented, and for some tasks. We talked about Moore's law, which is like 70% a year or something. But so anyway, capital gets more productive at 10% a year, and we have no more labor augmenting technology. That's his calibration, and that's what it looks like. So the growth rate ramps up, takes a while to ramp up, and the capital share rises to 100% over the course of, a generation or two. Okay, so those are the broad strokes of a shift to a world of growth substitution. Let's take a 10-minute break, and back here at 12:05, and then we'll talk about 5,000 other things. So by writing capital accumulation as a function of saved output, we've implicitly assumed that the production for capital is the same as that for consumption. Foregone consumption, taken, just like some of output that could have gone to consumption, is instead directed to increasing the pile of capital. So we just allocate fraction S of the factories, as it were, to making capital instead of to making consumption. And in this case, capital accumulation can drive growth if and only if it's a growth substitute for labor, like across the board, and that will entail a labor share that falls to 0, as we've seen. But more generally, this coupling is unnecessary. So Mukherjee and Ray have a paper from 2022, which kind of digs into all the ways that you could have a different production function for capital as for consumption. I think kind of just like the simple thing to notice is suppose we have gross substitution in capital production. So like robots build robots, and that's just a linear process. It's just, so you have exponential accumulation of capital, right? But in producing consumption goods, you need people. You need, some, I don't know, some service worker at the end of the line, packaging the consumption into a form that you like to consume or something, right? And for simplicity, I'm just assuming constant population, so constant L there. Well, in this world, consumption is going to grow at rate A times GK, and GK is growing exponentially, even with no new technology, because you have robots just out building new robots. So we can even get super exponential growth in output if A is itself growing. So, better than 1, 2, 4, 8, 16 robots. But the labor share is not falling to 0 in this case, because there's that step of the chain, toward like producing a consumption good you want to consume that requires labor. So labor is not a bottleneck to growth, but it is a bottleneck to consumption. And so you maintain high labor share and growth as fast as you like. Yes. Yeah, I mean, I think usually usually the reason for convex adjustment costs is that you're changing the kind of capital that you're building, right? Here, there's only one kind of capital. There's just bots, right? But it's a good point that if there's two kinds of capital, the stuff that complements the creation of consumption and the stuff that builds robots, then the fraction of your capital stock that you're having build new robots is going to be, that can just be constant over time. Yeah. See that? You could just always be skimming off 20% of your robots that are building new robots, diverting them to consumption, and so you wouldn't have an adjustment cost that's growing over time, even in that case here. So yeah, I don't think that would be a problem here. It would be a problem if you're trying to like shift ever more rapidly from producing some types of goods to other types of goods. And maybe in practice, that's what's going on if A rises. Like it's not just you're building the same thing more and more quickly, but you're in order to produce some kinds of capital that provide those services more and more quickly, you're changing functionally like what those machines are. So we're not getting into that, but yeah, depending on the details, I think it could bite or not. Zach?
I don't think we'll talk about capital adjustment costs until then, but when we do the gate model, we will.
Yeah.
And like they matter a bit for like thinking about short-term effects, but if you have these really strong long effects, it's not gonna happen.
That is also true. Thanks. Yeah.
Just to double check my understanding, this sort of labor share remaining constant isn't necessarily an interesting result, right? Because if it's called Douglas, it doesn't matter how the growth happens. Labor share is always constant.
The thing that I found interesting about it is that normally in Cobb-Douglas, if you have a Cobb-Douglas production function, labor, precisely because it's a bottleneck to the creation of consumption, is it retains a high share. But that means that a lack of labor or a lack of effective labor means you don't get explosive growth, right? The contribution of piling up capital to like further output diminishes because A is less than 1, right? I'm just pointing out that you can just separate the two sectors, and so you can have a lack of diminishing returns to capital in the production of more capital. So like naively, if you spend too much time with these models and you kind of don't remember this point, you could think that there's like a really tight logical connection between retaining a high labor share and slowing down growth. You can kind of see how the words might go. If if people are enough of a bottleneck to output that we can like stop up, we can stop up the gears and we can like demand a high labor share. If we're enough of a bottleneck, well, maybe that's great for like keeping our wages high and workers empowered, but the trade-off is that growth is going to have to be slow because we're a bottleneck, right? And actually, that's just not necessarily true. You could have just like capital piling up capital, and it's just explosive, and there's no labor bottleneck there. But then, in terms of like actually like siphoning some off to create some consumption that we actually value, labor is a bottleneck there. See what I'm saying? This is a pipe of capital getting big, and then this is the consumption. So you don't have like labor's a bottleneck here, but it's not a bottleneck in the feedback loop of growth.
Quickly follow up. Basically, but the labor share point is that if it's Cobb Douglas, the labor share is constant. If their growth complements, the labor share will go to 1 if capital.
Exactly.
And then if it's substitutes, it goes to 0, like almost like if it's any sort of like capital.
Exactly. So that's exactly what I'll say. So even though this is technically possible, and it's good to keep in mind, it's sort of knife edge. Okay. So that'll be maybe the second or third comment. Okay, first comment is that I guess you could see this as a limiting case of a tendency we've been seeing, which is for like manufacturing, the creation of new capital goods, to get more capital intensive. For the labor share, sorry, I said more capital intensive, but more concretely what I mean is for the labor share to fall in manufacturing, okay? But then when it comes to actually like, the kind of final point of consumption, people have been shifting over there, and we still like to use labor in consumption services, but yeah. So this combination of conditions in which you get fast growth because labor is not a bottleneck to creating the bots, but then it is a bottleneck at the consumption stage, relies heavily on that Cobb-Douglas edge case, as you were kind of noting. Okay, so if you have gross complementarity here, then the rate at which we can siphon off all of this extra productive capacity and turn it into consumption is like really hard bottlenecked by the lack of labor, right? So we actually don't get much consumption growth. Okay, so then people are a bottleneck in the relevant sense. And if you have gross substitution in the spigot, then the labor share is going to fall to 0. Right? So you need the AK and the bots, and then exactly Cobb-Douglas in the consumption. Yeah.
What's the point of working on towards a final consumption? That not?
Oh no, it goes eventually. It's just the point of building all these bots is that so you have more bots in the future to increase consumption with. You like C. C is the only thing you actually like.
So why would that not flow back to not producing so many bots?
What do you mean not producing them? Why not produce them? You have some. If you didn't tell them to build any more, putting aside depreciation, you're stuck at that consumption level forever. You don't have, K doesn't grow. You start with 10 bots. Okay, so instead of just getting stuck at 10 units of consumption forever, let's put aside 5 of our bots and have them make kids and grandkids and so on. They can do that really fast. They might even do that at a rate that rises over time. And that means that the rate at which, so with every new crop of bots, we kind of divert half of them, say, over to helping us make consumption, and then have the rest of them grow their descendants even faster, and yeah, it seems pretty good. Yeah. I think I think again, this is a knife edge case, but I think there are different like concrete scenarios that would roughly fill this. So it could be that people like all of the infrastructure that goes into making some experience possible, some like great like vacation or I don't know, just or even like grocery shopping or something. Like all the food's free, but you know, having a greeter at Walmart or something. It's just or it's, yeah, there could be some use for people at the end of the whole sort of supply chain when it actually kind of hits you. Yeah, I could think of better examples probably. You ask GPT for some examples.
CareWorks would be the standard one here, right? Like
What's that?
CareWork, you want to be taken care of by
Care work, yeah. But I mean, I guess, yeah. Yeah, maybe. Yeah. I don't know how, yeah. Broadly construed, I guess you'd be calling the L here care work probably often. So it's sort of knife edge. Still though, yeah, maybe another reason why it's good to know about like this being a possibility is that it might be important to know like when we're getting close to some closed loop in which capital can sort of self-replicate, whether or not it drives growth up or the labor share down. Like for military purposes, for instance, it's going to be really, you know, this is a very different world for military purposes, right? If like these are, you know, yeah, if you don't need people for the creation of drones or something. Well, yeah, we'll talk a bit more about that this afternoon. Okay, now we'll dig into wages a bit more. So we've got this robust point that growth would accelerate and the labor share would fall. And as we've been, so far it sort of looked like unless you're in the rho equals 1 case, wages would rise because capital and labor would remain complementary and you get way more capital, right? That's what we had seen. Yeah?
Should we consider that labor was like fixed, or was it?
Yeah, you can just assume that it's fixed. You'll find that you can have it grow and that's not going to change anything. Yeah. So if you're not convinced of that, you can work through it. But for intuition, assume it's fixed. Okay. Yeah. So far, the models have been suggesting that wages basically never fall and, in fact, rise super exponentially outside of an edge case. But actually, both cases seem plausible. And most people, I think, have the intuition that they would probably fall in the event of full automation. So we can pick apart what assumptions you need to get that conclusion. First, why might you think that they can't fall? So given a smooth enough two-factor production function, that's CRS and weakly concave in each argument, increasing the quantity or augmentation of either factor either has no effect on the marginal product of the other if they're locally perfect substitutes, or increases the marginal product of the other if they're even a little bit complementary. It's kind of what we've been seeing all along. The growing mountain of capital complements labor. Yeah, maybe we don't need to go through this, but here's just a proof that that's true. All right, you kind of get it. Yeah, they're a little bit complementary. So more A and or more K can't lower marginal product of labor. And I think anecdotally, this is basically why many economists have the intuition that rapid capital accumulation will raise wages, even if it's sort of accompanied by or even driven by an increase in substitutability. When people have so making matters worse, when people have the opposite intuition, this is often for a bad reason. And so the economist with this intuition can say, here's a flaw in your argument, and it is a flaw often. People will be thinking about what happens in partial equilibrium. That is, what if we automated like my job, but not any of the other jobs? And then you kind of think that the answer to that question, job by job, will add up to like what wages will be for everyone if you automated all the jobs. So to see the issue, recall the task-based model. Automating task I will mean that now the quantity of that task we can crank out is higher. We move up from like the water line to the land line for that task. So we have we automate something, we're able to do way more of it, and it'll lower the marginal product of that task. So it lowers the wages for any person who hasn't retrained yet and is still sticking around performing that old automated task I. It's a close analogy to immigration, I think. If you have a population, and then you have a population of immigrants that have the same skill distribution as the natives, so they're just perfect substitutes. Well, in a constant returns to scale world, wages don't change, at least once capital accumulation is caught up, so that you have all the factories complementing the immigrant workers next door to the factories complementing the native workers. In fact, if you have a little bit of increase in returns from specialization, wages will rise. They can rise even given constant returns to scale if the immigrants have a slightly different distribution of skills, because then there's room for gains from trade. There's going to be some comparative advantage. So all these things pushing toward wages not changing or rising in the case of immigration. But if the immigrants have a different distribution of skills and the natives don't immediately retrain, then the people who have the skills that are disproportionately provided by the immigrants are going to see their wages fall. So yeah, if they're all plumbers, then wages will fall for native plumbers at first. Kind of analogously, though we could spend way more time on this, but I'll just point out that people point out that once we introduced, not immigrants in this case, but cars, so something that could perform the task that horses had been performing, cars and tractors and trucks and so on. We didn't need horses nearly as much anymore because the marginal cost of maintaining a horse stayed the same, but the marginal product of transportation was way lower because we had this huge surge in our capacity to create transportation. So the number of horses per person fell sharply, and we just killed a lot of horses. I think the population of horses fell by 70% within, 15 years or whatever. There's some striking statistic you can look up. But then as we've gotten richer, it's sort of risen again, and they're just largely recreational. Likewise, with sailboats, right? We are kind of getting more of all sorts of goods over time, including sailboats, except that right when we introduced the steamships and so on, we needed way fewer sailboats. So I think it's not obvious what the rent on one person per person will be when, in effect, we're rich and people are like horses or sailboats, that we're just kind of capital that you don't need. We don't bottleneck growth. If we had no horses, it's not like growth would grind to a halt. But we'll just sort of be these antique goods, which will be providing a narrow kind of service that's kind of not that necessary on the margin, but we'll all be richer, and it could just cancel out, or more than cancel out. It's just going to depend on the details of the model. Okay. So all that said, there is also a good reason to think that wages would fall, but it would have to be something like this. It would have to be that technological progress can be labor depleting. So remember, the result before was just what happens if A and K rise and then B and L don't change. But we saw with the automation model that in surprising ways, a change in the production function can end up being, in reduced form, depleting to one factor or another. And here's a simple way to see how, in effect, you can get labor depletion. Suppose there are two sectors, a robot-only sector, in which capital just produces everything out on its own, and a Cobb-Douglas sector in which capital takes the form of equipment complementing human work. And firms are going to maximize output, and what they choose is Z, which is the fraction of capital used as robots. No. 1 minus Z, sorry. This is a mistake. Firms set the fraction of capital used as equipment. So this is equipment And then everything that's not used as equipment is robots. So Z star is going to be the value of Z between 0 and 1 that maximizes output. You can work out what that is, but rather than go through the algebra, let's just sort of see it visually. So you've got these two sectors side by side. The slope is A in the robot sector, or let's say the robot sector, and then you've got the like Cobb-Douglas equipment sector. So fixing labor, say A is a half, the total product of capital used as equipment will face diminishing returns. It'll be high for the first tidbits of equipment, augmenting all these people you have lying around, and then it'll fall. So you're going to use capital as equipment up to the point that the marginal product has fallen to A. And then beyond that, you're going to use any extra capital as robots. Okay, so what does that mean? Well, let's say you start out with only this much capital. Then you're going to use it all as equipment. Because even the last bit used as equipment is more productive as equipment than the first bit would have been as robots. But then as you accumulate more capital, eventually you're going to switch over to the robots. Now fixing A, you're not going to shift capital over from equipment to robots. You're just going to like stop allocating ever more capital to equipment. But if A rises, then what happens? Now you only want to use capital up to here as equipment. Because using capital as equipment's got to compete with like a better outside option. Every bit of capital you're turning into a hammer for a human hand is you're giving up more potential output on the pure, the capital only side of the economy. And as A rises and rises, the amount of capital you allocate to augmenting people is going to fall and fall. And so wages fall to 0. And when you solve for Z star and then you plug it back into the production function, you find that once you cross that threshold so that you want to be splitting your capital across the sectors, in effect, this whole thing reduces to an AK plus BL economy, but where the coefficient on labor actually falls as A rises. So whether wages actually rise or fall, yeah, right? So we kind of see how this amounts to labor depletion in closed form. Increasing A, the productivity of the robot sector, lowers the marginal product of capital. Of labor. Now wages can still rise, and this is going to be the threshold where like we can make the factory sector with the equipment. We can make that more efficient over time as well, and that'll be a force raising wages. And it doesn't even need to rise all that quickly necessarily, depending on the exponents. So it could be that the factories are getting more efficient over time at like 5% a year, and the robot world's getting more efficient over time at 10% a year, and alpha's a half, and so wages are flat in that case. You can just work through the algebra, but yeah.
So intuition. B about A, it's because there's no more investment going into B.
No. So B itself is constant. So like this literal B here, we're holding this B constant. But when A rises, the optimal allocation of capital will shift over to the robot sector. So Z is going to fall. So if we have B tilde, which is like the actual thing multiplying labor, and that B tilde is composed of the B and the ZK, that is going to be falling because of the Z falling. So in like closed form, the level of labor augmenting technology is going to be falling actually. But it's because of this reallocation. Now, where do wages stagnate if we actually do get to the AK plus BL world and we stop developing more ways to make people more efficient, right? So like as we've just seen, one way or another, we could wind up in this perfect substitutes world, but that doesn't actually tell us anything about what wages would be. Or even whether they'd be constant, right? Because you could be in a perfect substitutes world, but just like the shape of the production possibility set could evolve over time in a way that means that the marginal product of labor actually falls rather than stagnates. But anyway, even if it stagnates, we have no idea where it'll stagnate. Yeah, there's a paper that y'all might have seen by Anton Kornek and Donghyun Su, in which they basically start out with a CES production function and imagine what happens as rho goes to 1. And they conclude that wages would be low. They're doing this within the context of a task-based underpinnings for that CES, kind of like what we saw on Monday. But again, to reference another exercise, the one from Monday, I think, you could just as well study what happens as you approach perfect substitution, fixing like little a times a to the rho rather than fixing little a. See what I'm saying? Like, because perfect substitution is not like a point, it's like a range of scenarios. And so you can like you can trace your path to that range in different ways. And yeah, this is the exercise from Monday. This is why I thought it was going to be relevant. So what's going on in this graph that we've already seen before is that as you automate more tasks and like in that sense work your way to the finish line of AK plus BL, perfect substitution, wages rise at first for the standard like dirt and water reasons, but then they fall once you cross the automation condition where the water is spilling over the land, and so the marginal product of labor is low now because every drop of water has to fill the whole tub rather than an ever narrowing strip at the right edge of the tub. So wages fall in their calibration. They fall once we hit 90% of tasks automated, but that'll just depend on like the there's not like a certain number of tasks automated that'll cause wages to fall, because if the rate of automation is constant, then wages just rise indefinitely, right? So it's the point is that the proportional rate of automation grows, and it happens to be growing so fast that we cross the automation condition in their setup. We start growing so fast in proportional terms right around where 90% of the tasks are automated. So that's kind of what's going on with this graph. And then they find wages end up being low. And yeah, I mean, I think it's qualitatively true that this can happen, but there's basically no way to just say from first principles what the coefficient on labor would be in a full substitutes world. It's like, what's the nearest possible world in which we have full substitution? It's a little undefined. It's like these counterfactuals that are always a little undefined. It's getting philosophical, whatever. Like if Mozart hadn't been born in Germany, what country would he have been born in? Okay, so all right, now so far we've been thinking about we've basically been thinking about an exogenous shift to a world in which capital and labor can be gross substitutes. We sort of deviated from that a bit when we talked about this world, where once A gets high enough, we shift over from the Cobb-Douglas scenario to something like a gross substitutes scenario. But here's kind of a little bit more on how that can work. Suppose there are, again, those two uses of capital as, here I got it right. So here where, yeah, Z is equipment, 1 minus Z is robots. Yeah, don't think we have time and maybe it's not worth it, but the lesson here is going to be, let's say we could, instead of using our capital as equipment, we could turn it into robots that perfectly substitute for labor as well. Or we could turn some of it, depending on where we set Z, into robots. How many robots we get from giving up a bit of capital, that is like diverting a bit of output away from either consumption or augmenting capital, how many robots we get is theta. See that? Because 1 minus Z times K is the amount of capital we put into making robots, and for each unit of capital we put aside to make robots, we get theta robots. Okay. So, and how valuable is each of these robots? Well, it's going to be the same as the marginal product of labor, right? The marginal product of labor is going to be the same. Like you've got, yeah, feeding into this part of the production function, you've got the labor and the robots, and they're each, the marginal product of one is going to be the marginal product of the other. Now, before we're building any robots, this is just a familiar old world. It's like the Solow model, and technology is growing and capital is growing alongside technology, and wages are rising exponentially. And because wages are rising exponentially, but the cost of a robot is fixed with no new technology, eventually it becomes worth it to start building the robots. Does that make sense? So maybe like we don't even need to do any new technological development. Maybe in some sense we already know how to build a robot for like $1 trillion, and with wage growth, with eventual, once we're all making like $1 trillion per lifetime, we'll just switch over to the robots, to making robots. That makes sense? So we don't necessarily need to invent cheap ways to build the robots to switch over to a world of gross substitution. As long as they're feasible at some cost, they'll eventually be profitable, given wage growth. And in fact, once they become profitable, they'll become ever more profitable over time. Because if you try to like suppress the building of the robots, you're suppressing the replacement at fixed cost of something, human work, which is itself getting ever more expensive. And so, yeah, it's going to be hard to steer technological development in a labor augmenting direction permanently, like in a way that kind of keeps the labor share high. I think, yeah, people are valuable, and that's sort of our own undoing or something. Yeah, sure enough, you see automation and robot usage in particular much more widely in high-wage countries, as you would predict, and there's lots of evidence that wage growth, in fact, causes automation, and there's different models of how that can happen. Now, on the pure version of this story, once we start building the robots, wages don't fall. Wages rise up to theta, at which point it starts becoming worth it to build the bots. And then they stagnate at theta. Does that make sense? Wages won't then fall, and if they fall too much, then we just stop making the robots again. But if we get more productive at building robots relative to other things, but it takes, like, we're giving up fewer units of other sorts of capital, or fewer units of consumption per robot built, then wages can fall. And that's kind of the first thing I have to work out. Just to like flag it again, I know some of you are really interested in it. This section is called endogenous automation, and I've just been talking about like endogeneity via factor prices, but political economy is also endogenous, and we'll say a few words about that later. Okay. Let me actually come back to the fixed factor thing this afternoon, and instead very briefly tell you about what actually has been happening to some of these macroeconomic variables. So yeah, as we saw a bit of yesterday, especially from Bharat, there's at least some evidence at the micro level that we're seeing AI kind of automate some kinds of work. And as Zach kind of gave us a literature review of AI being kind of used across a lot of kinds of work, but it's all been very microeconomic. And you might ask whether we're starting to see any like first glimmers of a shift to the world that I laid out at the beginning, and that some people think could be fully implemented within a few decades. So in 2021, Nordhaus has this paper pointing out that kind of what we've just been seeing, you would expect to see rising output growth, rho starting to creep past zero, a rising capital share, in or approaching a world of full automation, or of gross substitutability, really. He also proposes you would expect to see a rising share of IT capital in total capital if the kind of main mechanism is that IT capital, like smart robots and just AI in general, is accumulating fast and not going the way of Moore's law anymore, but staying, like the price isn't falling. So the share of GDP is actually rising, and GDP growth is getting pulled up by the huge quantity of this kind of capital because it's able to like substitute for labor ever more. So anyway, so he thinks a rising share of IT capital in total capital as well, and rising TFP growth, because of the fact that TFP growth is this weighted average of the GA and the GB, but GA could be way higher than GB is currently, with kind of Moore's law maybe as a motivating example. He also proposes we'd see a rising capital to output ratio, and I think this is actually totally backwards because, okay, maybe in the short run you'd see a rising capital to output ratio as we pour a lot of capital into investments that haven't paid off yet, as Eric was telling us. But let's say we could observe the intangible investments, then for a while, in the first part of the J curve, you'd see, you wouldn't see output rise, but you'd see capital rise. But in the long run, just y equals AK with rising A means a capital to output ratio that's falling to zero. Each robot is building more and more units of capital, so capital divided by output is falling to zero. Nordhaus says you'd see a rising amount of mismeasurement, but of course that's hard to measure by definition. Okay, there's also a few other things you would expect to find. So a rising labor productivity number, output per unit of labor would rise both because output would rise and because labor at least might fall. You'd see rising interest rates because mechanically the interest rate will equal A, and if A is rising, then yeah. It would also happen in a more subtle way because, as we were seeing, if people are anticipating much faster, like much higher future consumption, if you're anticipating that your consumption will be much higher in the future, you need to be compensated with way more dollars in the future per dollar you give up now for the margin utilities to be equal, because your marginal utility will be falling really fast. And Zach will have more to say about this on Tuesday. And yeah, probably rising energy capacity and usage. Obviously, the bots run on electricity the way we went on food, but then more concretely, like just data centers are famously energy intensive, and yeah, and like most resource usage in general is energy, basically. Whatever. Okay, so here's some graphs. Well, GDP growth flat, growth substitutability between capital and labor. Basically, no, it's still, at least unless you go the Piketty route or something. If you ever thought it was gross complementary, you still think it's gross complementary. The capital share has like maybe risen a little bit over the last few decades, but this is easily explainable in other ways. For example, due to firms having rising market power or something, rather than some like deep change in the shape of the production function. And it's just such a slight trend anyway. The share of IT capital and total capital has actually gone the other way. You can't really see the trends in the lower lines, but they're all trending downward. Even as we get more and more computers every year, their marginal value, their price is falling more quickly than their quantity is rising. And as a share of GDP, IT capital, or as a share of capital, IT capital has been falling. It's gone the other way for software. So that's kind of maybe a trend in the right direction. Output per unit of labor is also basically flat, whether or not you make various adjustments for utilization. Oh, sorry, that's TFP that's been flat, but labor productivity has also been kind of flat overall and actually declining, or the growth rate of labor productivity has been declining for, if you're looking at like how many, what the dollar value is per unit of labor in the creation of computers and other electronic products or semiconductors. So we're not getting close to like automating those supply chains in particular, basically. Like people, yeah, or we're not accelerating the rate at which you need fewer people, fewer hours of work to create a unit of output there. Interest rates sort of wander around, but no, hockey stick or anything. Energy usage in the US has been like remarkably flat for a long time. You hear people complain about this a fair bit now, like you just compare the US and China or whatever. And yeah, for whatever reason, GDP is growing, but we're getting less energy intensive, and energy consumption's been flat. This is overall energy consumption, including like electricity and combustion. If you just look at electricity, if you think that that's more relevant to AI and sort of future tech in general, you find that generation has also basically been flat and capacity has risen, but this is basically because for wind and solar, you need more capacity per unit used because the output fluctuates so much. So yeah, to recap, yeah, with growth substitution, you're going to see a lot of growth. Labor share probably fall to zero, except in that edge case where the robots build robots, but you need the care workers or something at the end of the line before they turn into consumption. The intuitions for how all this will work are basically just like your intuitions for the perfect substitutes case, except for when it comes to wages, where wages you would think would be constant in the perfect substitutes world, but actually what happens to them is really sensitive because it basically got these two robust things, right? Growth growing really big, labor share falling really fast. And so what happens to the products can be really sensitive to the details. And in particular to how we reallocate capital between labor augmenting and labor substituting uses. We didn't talk about the fixed third factor stuff. I'll try to get that in this afternoon. But at least on my reading, even though we could well be near an automation-driven growth explosion where near means, I don't know, within a decade or something, because the world can change quickly in principle, you really shouldn't be claiming that we're seeing any evidence of it in macroeconomic data. Okay, thanks.